Hello everyone and welcome back. So today we will be writing a simple program for multiplying two numbers using 8085 assembly language. So why I took up this subject is that I felt that maybe we can approach this problem in a different way and also learn some important software development and programming principles using this example. So let's begin. I'll just type out what are we going to do here. So multiplication of two numbers. So first of all, you will notice that we are saying that we are going to do multiplication of two numbers. We are not saying how big are those numbers. Okay, so we are keeping the requirement at this stage a bit vague. We are not starting with very strict requirements because we want our program to evolve. We want even the requirements to evolve. That is how real software development happens, not only in terms of what you get from outside, like what you get from the user or the product manager, but also in terms of our own knowledge. As we work on the problem, our own knowledge about the problem evolves, and so does the software itself. So that is how we are going to start. Now, to do multiplication, first of all, it's always better to start with some examples if you have them. If the problem that you're solving, if that problem has some readily available examples, always start with them. At least start thinking with them. How would you solve that particular problem for that particular data? So we'll take the simple a simple example of 2 multiply 3, and we will start to explore this. We will start to explore this example and think about what does this mean, what does this say, what are the terms that are being used here. One of the ways in which we say this expression is that 2 times 3, right? We don't write this way, but we do say it this way, and this is a very important thing. How are we talking about the problem? So as a software developer, you have to notice that. You have to hear these different terms that you are listening to when you are in a meeting, or when you are with a user. The user is describing the problem. You must pay attention to these special words that come up in that discussion and note them down. What do they mean? Okay, we also say that 2 3s are. Okay, so we sometimes write, we don't write, but we say it, and this is how we as kids memorize the multiplication tables, right? 1 3s are, 2 3s are, 4 3s are, and all that. So this is also something that we must note down, that yes, this is a term, that is a phrase that is used in the problem domain. Okay, great. So now that we have these two terms, we can think about how do we do this. How do we do multiplication? Because programming is all about hows. HOWS, how. So programming is about representing imperative knowledge. Imperative knowledge means how to do something. We have to write a recipe. That is an imperative knowledge. So step by step directions, and that's an imperative knowledge. So how do I reach from place A to place B? There are step by step instructions on Google Maps. So that is an imperative knowledge. So we need to describe the process of multiplication. And since it is multiplication, it is well known, and it's also how kids are taught. or introduced to multiplication is that multiplication is repeated addition. This tells us, this defines multiplication, but in a how-to way, how to do multiplication. Not only it says that what is multiplication, which you may see in some higher maths book maybe, but I don't know that. But in this definition, it says not only what is, but how we do repeated addition, and then we actually will be doing the process of multiplication. This is the name of that. So great. By the way, just as an aside, if you are interested, think about this and also search for it, is that if we are saying multiplication is repeated addition, then is addition repeated something else? Yes, it is. So repeated addition is repeated succession. Succession means plus 1. Okay, so succeed means plus 1 plus 1. So 1 2 3, it's basically counting. Kids learn 1 2 3 4, and then they're introduced to addition, because addition is, if you do plus 1 5 times, then we say do plus 5. Addition is repeated succession. Now the next step is multiplication is repeated addition. Okay, good. What is the next step? What is repeated multiplication? It is exponentiation. So exponentiation is repeated multiplication. Great. Is there something which is a name given to repeated exponentiation? Yes, there is, and that is your task. Go ahead and search that on YouTube. Watch some videos on that. It's interesting, only if you're interested. That's a optional thing. So moving on to how we are going to write the code. So we haven't started writing the code. So what else is required before we can start? So we took an example, right? We took an example where one of the numbers is 2 and another is 3. Great. What do we call them? So in the program, let's say, okay, we are working with 2 and 3, but we can't write 2 and 3 everywhere, right? We have to use some kind of an abstraction, some kind of an abstract name for both the values. Now, one way is just you can name them A and B, or if you don't like A and B because they are the register names, you can use X and Y. Maybe we can use those names. X is 2 and Y is 3. Yeah. So, but they don't convey any meaning in this for this problem. X and Y is too generic. Can we have some better names? Always search for better names. If you can't find any better names, yeah, we can fall back to A, B, C, X, Y and all that. But if you can, use them. So that's always a good thing. So what better names are there? So in this for this problem, it's readily available. So we can say, or we say that there are two terms. One is the multiplier. Okay, so multiplier is the number which tells us how many times to multiply or repeat. Okay, I'll use the term repeat, because otherwise we'll be using multiply too many times. There is another term which is the multiplicand. So multiplicand is the number which multiplies. Okay, which multiplies. So here I am using the word multiplies in the sense that it's like the virus multiplies. So the number multiplies. So from 1 it becomes 2. So like 3, it becomes 3, right? So it was 3 and then we say 3 plus 3. So it has become 2 now. There are 2 instances of that, of 3, you can say. So how many times? 2 times. And which number multiplies the 3? So they have names, right? We have now names which are multiplier and multiplicand. This will be important. So now we can name this. We can start writing some code, and since we can name them, we can say that multiplier equals 2 in our case. Why? If you say why is 2 multiplier and not 3, we have written it that way. We have taken up this example in such a way that we are saying 2 times 3. So 2 times 3. Okay, we are saying repeat 3 2 times. So that is why we are using 2 as the multiplier. We can do it in the reverse way because multiplication is commutative. But we'll come to that at the end of the video, like how do we decide which is multiplier and which is multiplicand? And that comes to the at the end. Okay, so the multiplicand is 3. Okay, so we have these 2 constants. So with these constants, we will start writing the rest of the code. And what do we start with? You may think that we'll start with maybe some input and all, and then we will have the numbers, but we already have the numbers. This is a good thing right now for us, because we don't need to think about where do we get the numbers, where in which memory location is that stored, and all that. We have already defined constants. We are working with an example. We can directly jump to the core logic. So this is another thing that you must always follow, is that whenever you are writing some software program, whatever, it does not matter how big is it, focus on the core of the problem. Solve the core problem first. Everything else comes later. Input and output in this program is not the core. The core logic is the process of multiplication, and that is what we are going to implement next. How do we start this? We can look at the definition again, which says multiplication is repeated addition. So there are 2 terms here which we can use for our implementation. The terms are repeated and addition. Now we have to do both of these. So let's look at this one by one. So addition, can we do addition in 8085 assembly language? Yes, we can. There are many such instructions which allows us to do that. So great. Can we do repetition? What is repetition? Repetition is a way of doing something again and again, right? And to do something again and again, we need language support in some cases, but do we really? If you see in all the languages, we usually have things like for loops and while loops and many other kinds of loops. But really, if you see, we do not need any kind of special syntax to do repetition in any language. In assembly language, how we do that is using the jump instruction. Okay, or rather in the conceptual sense, it's a go-to. So if we have jump, we will be able to do repetition. Okay, so now we will start writing the loop. Now in repetition or in loops, there's always some kind of a state that has to be maintained. Okay, whether you maintain it explicitly in your program or whether it is maintained internally by some internal code, or it is maintained by let's say the interpreter, the runtime, does not matter. Maybe In cases like recursion, it's implicitly maintained by the stack itself, the call stack. So but there is some state, there has to be some state which will evolve in each iteration. So this is the basic of any loop. If you have to write a loop, this has to be there. Okay, if you are doing recursion, that loop is implicit. If you are not doing recursion, it's a iterative loop. It will be explicit in your program. You will be able to see that. So what kind of state do we need right now? So let's say we are doing a countdown. Okay, so that's how we will look at it, or a counter you can say. So we'll be doing a countdown from what? From the starting from the multiplier. So we'll say let's use the register C for counter, and initialize it to multiplier, the initial state. Every state, again, whenever you are doing some kind of state in your program, it will have a starting value, it will have an initial value, and then it will evolve based on some rules which can differ in based on what kind of state it is and what kind of process is it involved in. So in this case we have initialized the counter state with multiplier. Okay, now next what do we do? Next we start writing the loop. In loop, what do we have to do? We have to do something, we don't know what. We'll do something, and then what we'll do, the state will evolve. Okay, so the state will evolve to, in this way, it will decrement. So we have done that step, we have do something in return, which means we have done that step now, and we are decrementing C, counting down. And now we go back and start a new iteration. For that we have to jump to this label loop. To jump to that label, we have to do a jump, but conditional jump, right? We can't keep jumping because otherwise it will be an infinite loop. So condition, what condition? When the countdown is not 0, so when the counter is not 0, then we go to loop. Okay, halt. So halt. This is because of that, for the next step. The next step is, once we have written this code, the next step is to test. We have written some basic logic, however simple it is, but it's some logic, right? So we must test it. How do we test? We'll just run it. What do we expect to see? No change. Why? Because C will start with the value 2, and then we will decrement it, and it will go back to 0. It is already 0, it will stay 0. So let's see if that happens. Yes, it happens. So as we see, no change in C here, so it stays 0. Now I think that is not very, you don't feel confident maybe looking at this. Like, yeah, it was 0 and now even now it is 0. So did it really do anything? I don't know. And unless you debug it, there's no way to see that that is happening. The loop is actually happening. So if we want to see it, what we can do is we can add another state, which will keep the count of how many times the loop ran. Okay, so we will say we'll keep another state in the accumulator, which starts at 0 this time. Okay, and we will count up. So now we will do something inside the loop. which is not just evolving its state, but we are keeping another counter which we will increment. If we do this, we should see a being 2. Why? Because this loop runs 2 times, so a will be incremented 2 times. We should see 2 here. Let's do that. Okay, so we have 2. Great. And now we move on to the next step of actually doing multiplication, at least for this example. At least we are doing 2 times 3. We are not saying we are solving multiplication for for many numbers or for many different numbers. We are at least doing it for these two numbers. The next step we'll take is the doing the actual multiplication. Okay, so to start doing that, what we will notice is that we have to do addition. We are already doing the repetition part. We have that part of logic working. We need to do the addition part. So here, between the start of loop and this part, which is the loop mechanics itself, we have to do something. We have to add, but we are already adding. INR is addition, but we are doing just +1 rather than plus the multiplicand. So we just need to change how, or rather what number we add, and that will be done using this kind of code. Okay, so now if we run this, let's see, we should see 6. Yes, where there is 6 in the accumulator, which means we have done the this part of code correctly. We can quickly check certain things like, yeah, so things like 2 and let's say 5a. So we can do some more testing and so we can feel more confident that it is doing what we want it to do. We can test more numbers and see that. Now from here we keep testing. Okay, we keep testing, and let's say we are testing something like some big numbers now. Okay, we test this 1 times ff is ff. Great. So at least, so that is working. Now we do 2 times ff. Okay, so if we do 2 times ff, uh, is this the answer? It cannot be fe, right? If you multiply if you add ff and ff, it cannot become less than that. so 2 times ff is, I can, let me see, so 2 times ff is 0 1 fe. Okay, so that 0 1 is missing. There's no 0 1 because we haven't tracked that. 0 1 is the higher byte. There's no higher byte anywhere. We are not doing anything like that. A overflows, register A. If you keep adding ff, it will overflow, and then obviously you will not get the rest of the result. The higher byte is lost. So we need to handle that now. So we have found an example which now tells us that our logic is incomplete. We have not written the full code. So how do we do that? So let's think. We are adding stuff. Okay, we are adding the same number multiple times, and at some point there's not enough space. Here by space I do not only mean memory space or bits and bytes. So what do I mean? Let's say you are adding 1. You keep adding 1, start from 0, you keep adding 1, 2, 3, you reach till 9. But now 9, if you add 1, you will get 10. What do we see is that there is not enough space in the ones place to store 10. So what do? We move the we reset the ones place, and then we go to the tens place. And what do we do to the tens place? Well, we do something, we write 1 there. But is that what we do? Let's continue this process. After 10, let's say 11, 12, 13 till 19, and then again we reach 20 if we do plus 1. So what is happening? If you see that the higher part of the result, we are just adding 1. So earlier it was 0, we did plus 1, it became 1. So 10, 11, 12, so it was 1, 1. And then when we reached 19, we did another plus 1, and then we reached 2. So 20, 21, and so on. So whenever there is an overflow in the ones place, we add 1 to the tens place. That is how addition is working. So here too we are doing addition, right? So that logic should be similar. We should be able to do that now. But we only need to do that if there is an overflow. So if there is no overflow, there is no need to do a plus 1 on the higher byte. Now, there are two things. First, we have to track that higher byte. Okay, right now there's nothing in the program that indicates that we are tracking it. So first, if we need to track something, we need a state. So let's create a state, and we say that this is the accumulator has the lower byte of the result and lower byte of, sorry, this is the, so, and this is, and B would be the higher byte of the result. Okay, so what are all these? These are the states which we are maintaining for this program. So now that we have a state to track the higher byte, we have to increment it conditionally. So if when overflow, then what we will do is we will do INR B, and otherwise we will continue. Okay, continue the loop. Now we need the actual condition, right? So we need like check overflow. How do we check overflow? So in this case, if if there is an overflow, since this is an addition, the carry flag would be set. So we can use the jump carry or the jump not carry instruction in this case. So we will use the jump not carry instruction and say no overflow happened. Why? Because then we can jump over this part, this then part, and directly go here. Okay, so if there is no overflow, just continue the loop, and if there is an overflow, we'll first do INRB and then continue the loop. Okay, so this should give, at least solve this part. Let us see. Yes, so we have B as 0, 1 and the lower byte as FE. So at least this example is now solved. Now that we have multiplication working, for the full 8-bit numbers. So we can say that the problem was about multiplication of two 8-bit numbers, not just any numbers. We are even specifying the problem much better. Not only we are improving the solution, and it goes in cycles. We know, we come to know something about the problem, we do that, we write some code, we test it out, and while testing it out we see that, oh, something is missing, or this part of the problem is not being covered. So we make that part explicit in the problem statement, and then we go ahead and fix that. So now that we have, by the way, we should actually do much more testing. Okay, we you can't just rely on one pair of number and say that, oh, I have done the logic correctly. So you must do much more testing, so that you can be more confident of your solution. The next step that we are going to take is, now that we have things working, we'll look at refactoring this code. Okay, refactoring will help us in the coming steps. So everyone's favorite, I think, would be how to take input and read from memory. We want to do that because we are still working with the hard-coded numbers in the code. So obviously we have to read from somewhere. But before we do that, if we start writing that code right now, we'll probably write that code somewhere here, and then we will store something here. So where is your core logic? That will get lost. So core logic is here, right? That will get mixed up with all the input output things, and anyone who is reading your code will not be very confused, because since this is a small program. But in a larger program, this kind of mixing up things, mixing up your different layers of your solution will make the program or the software easy, more difficult to read. So you must not only write your code for the machine, but you have to write the code for other human beings. Your code should be readable for human beings, not only for machines. Machine will tell you anyway. There's no escaping the machine, that I will write anything and the machine will execute it. No, that won't happen. It will say the result will be wrong and all that. So, but the poor human beings, they will not be able to say. Maybe they'll feel that I am not a good programmer, that is why I can't read this code. The other person was more intelligent. But that's not how it works. Uh, if someone is a really intelligent programmer, their code would be so easy to read that anyone can read that, even a novice. So we must make our code much very readable. We must optimize it for reading. So how do we optimize this? How do we keep our core logic separate in a module, and still add input output later? Since this is assembly, we don't have many options, but we have some things. I mean, there are things like you can write multiple files and all that, but here we are going to write only one file. So what we can do is we can create a simple function. So we can create a function multiply, and then we will specify what this function is about. So we will specify that this function is called multiply, and it's supposed to multiply to 8-bit numbers. Then we have to mention that what are the inputs that are used by this method. or the function or subroutine, whatever you want to call. So the inputs is, what are the inputs? Let's see. One of the inputs is the C, the register C, which takes the multiplier. So C, we can say multiplier. Okay. And then what else is there? We have the multiplicand, but the multiplicand we it's hard coded right now. So now that we are refactoring, it's time to remove these hard codings. It has served us well, it has helped us write our core logic, that's great, but now it's time to move on. And for that we need to store this multiplicand into some register. So let's say we do D, just like that, and multiplicand is expected to be in the register D. Then we say what are the outputs, where are the outputs? So we say A, the accumulator has the lower byte and the higher byte goes into B. Great. So if there is anything special about this, maybe it destroys some data, writes to some memory specific, or does all that thing, you can write notes below this, like notes or description, things like that, and make it more clear. That would help. So now with this, we can actually modify this code, or rather what we will do is, first we will get rid of, no need to get rid of this, let's delete it later on. We will write jump start, because we are going to write some code which uses this multiplication subroutine. Someone has to call it, right? So we need some code to do that part. So to do that, we will say call multiply, but that's not enough because we have to send in the input. So we have to do this here, and we have to do mvid is multiplicand. Okay, if we do this, then this has to change. If we are saying that the multiplicand is in D, then we have to do add D. Okay, so let's see if this is working. I'll just clear these registers and flags. Okay, so we will try to run this program. Anything that I've missed is like, so takes NV state, add D, and jump. Oh, so this now, since this is a function, we have to return from that function. So I have to write a return, and then the inputs are the same. Let's try this. Yes, so this is still working. So we have the higher byte 1, lower byte FE. So that's fine. So now we are at a position where we can start with the input output part. Okay, so first of all, we will just comment these out, which means that this part is no longer working, and we have to decide where will we read it from. So we will modify the problem statement, which says that multiplication of two 8-bit numbers, we will now say stored at 2000 and 2001. Okay, and we'll also say the result should be stored starting at 2002. Okay, so now we have to take these addresses and we can do it in many ways. I think I'll just do some LDA load accumulator from 2000, and this should go to the register C. Similarly, I'll do move D, and I'll do LDA but 1, and then we will call the multiply subroutine, and then you have to store at 2000A, so we will do STA 2002, and then we'll move B into A, and then we will do STA 2003, and then we will test it. So to test it, we will go to 2000 till 2003. Great. So now we can do 2FF. I'm using the same example, if you see right now, because I've changed the code to take input from some location. I've changed a lot of things. So I don't want to really change the example to write, because then if there is a bug at this stage, I won't know whether it is a bug because my core logic does not handle those numbers correctly, or is it some problem with the way I'm taking input. At this stage, do not change the inputs, keep the input same. Once you have verified that yes, this part of taking input and writing the output is working fine, then we can again test with other numbers. We can continue our testing of the core logic. Okay, so we have 0 1 and FE. Great, so that part is working. But I don't know, I don't like hard coding this kind of things in my code. I mean, I will have to hard code it somehow, but what if I could write, I could write multiplier address is 2000, and then we say the multiplicand address is 2001, and the result address start is 2002. Okay, great. So I can use these labels now rather than directly the address values, and this would be +1. I'm using a similar level expressions here, so we can do that. We will just clear the memory, and then we will write it down again. Hopefully this will work. Yes, it is working. At this stage, probably what we'll do is we'll keep testing for more numbers. We will try to clean up the code if there is something that is not required and all that. We can keep doing that. Now there's one thing that I want you folks to consider and think about and probably solve. Okay, so what we did here, if you see in the problem statement, I've written two 8-bit numbers stored at 2000 and 2001. Okay, great. But in here in the code, that is not what I'm writing. I'm not treating 2000 and 2001 equally. One of them I'm saying is the multiplier, and the other is the multiplicand. So they are not equal in terms of the logic inside the program. They are treated equally at the problem statement level. So there is, how do I choose which one is the multiplier and which one is the multiplicand? So that's something that you must think, and something that you must fix. As you saw in this video, we didn't just write the code. What I have tried to show here is that how we think about writing programs. Okay, this was a very small program, but still we can apply the process of thinking through it, and a lot of this that you have a lot of the process that you just saw can be applied to software at any level. It does not matter how big that software is, what kind of problem you are solving. you know uh, it does not matter how big that software is, or how complicated it is. You can always use these basic principles to get started, and to write your code. Also, something you might have noticed is that we took very small incremental steps in writing our code. It's not that, okay, we start from we specify the problem statement, and then we start from the top, and we write the whole code line by line, and that's it. It's done. It's perfect. It'll never be like that in the real world. You will not start, you know, and be able to complete it in one go, or even in like few days or something like that. Your software should grow, organically. You would come to know things about the problem, and then you will modify your software to handle those that extra knowledge that you have gained. Okay, and it is possible to gain that knowledge by the through the software itself, through testing itself, through observation. So you will come to know of many things when you see your users use your software. You will see that there are bugs. You will see that, oh, this is not really helpful, or maybe we can do this in a different way. All this you will observe, and your software would uh, evolve. But even before that, even before you take that feedback, you have to take your own feedback. When you're writing the code, you write a small step, you test it. It does not matter if it is automated or not. It's better if it is automated, but even if it is not, you must test the code through some manual testing, check it, and then go to the next step. Okay, so, and let it grow. Like, we didn't write this overflow logic in the first go. We started simple. Start with simple data, start with simple examples, and then add more and more complicated things as you come to know about it, and as you go through evolving your program. That is how any software is written. And I also hope that you have enjoyed this video. So if you like this kind of video, please let me know in the comments what other such videos maybe you like to see. Maybe some other program that you want me to write in this fashion, so that we can go at it step by step, and learn some more deeper things. So thank you, and goodbye for now.